Good morning, everybody. Before we start, I was made aware of a problem with the problem sheet. This is problem sheet number 1. And there, in problem number 4, part B, there was a sign error that I now corrected. So as you see it now, it's correct. As it was there, it was wrong. There was a plus sign. And then, this is the Grassmann identity here. And there was a typo, such that the result would have been exactly 0. This is not always correct. As it is now, it should be correct. All right, sorry for that. I hope it didn't cause too much confusion, because I'm sure all of you looked at these problems already. All right. Let me briefly summarize what we did last time. I said we need Larmor's equation as a foundation. What does Larmor's equation say? It tells you what the radiation power of an accelerated point charge is. Let me just write down Larmor's equation again. First of all, because we will need it. Second, because it's beautiful. Larmor's equation. We had 4 of them. All right. The differential version, right? So the radiation power emitted into solid angle element d omega for a relativistic charge that was given by this beautiful expression here. Remember the notation, E hat is a unit vector pointing from the charge at the retarded time to the observer. The right-hand side needs to be evaluated at the retarded time, so at the time when the signal is emitted. And we deviated from that when we calculated spectra. I will return to that. So that's the full relativistic version. If you integrate this over solid angle, you arrive at this. You arrive at this version. Thank you. All right. This is the full glory, right? This is the fully relativistic version. We are going to need this afterwards in order to calculate the spectrum of a synchrotron source. Very important for astrophysics. We get to that. So we will need the fully relativistic version as well. However, for many circumstances, the non-relativistic version is enough. And then we said, okay, I can approximate this beautiful term here by 1. I can neglect the beta compared to the E, and I get this very much simplified version here. And if I want to know the total power in the non-relativistic version, I can write it like that. We will need all of that. We'll make use of all of that, right? And because these equations are so important for us, I sketched how they are derived from Maxwell's equations. And the whole problem sheet is focused on tracing these steps, right? How to arrive at Larmor's equation. What was the point? We started with Maxwell's equations as an expression for the vector potential, or for the Four potential. We used the Green's function of the D'Alembert operator to invert that equation or to solve that equation. We arrived at a general expression for the potentials. We inserted the electric current density for the point charge moving along a trajectory, got the Liénard-Wiechert potentials, converted the Liénard-Wiechert potentials to an electric field, inserted the electric field into the Poynting vector, and we're almost there. All right. Then we used the non-relativistic version of the differential Larmor power in order to calculate the Thomson cross-section in three different versions. First of all, the polarization-sensitive differential Thomson cross-section, the polarization-averaged Thomson cross-section, polarization-averaged differential Thomson cross-section, and the polarization-averaged total Thomson cross-section. The final result of that was that the Thomson cross-section is given by 8 pi over 3 times this strange classical electron radius, where we saw that this quantity here, of course, in the only useful electrodynamic units, has the dimension of a radius. This is 2.81 times 10 to the minus 13 centimeters. This is 6.6 times 10 to the minus 25, if I'm right, centimeters squared. And this is a quantity that will reappear everywhere. All right. Do we have questions up to this point? Do we need to go through some of the arguments again? Not the case? Boring? All right. Then let me return to what we started saying about spectra, calculating spectra. Right? The key identity that we used was Plancherel's identity, right? The Plancherel's theorem. And in a slight misuse of notation, I used the same symbol here for the electric field and for the energy. Now it's the energy. And I said, okay, if I want to know how much energy is radiated, how much energy, total energy, I need obviously to integrate the differential Larmor power over time. Then I inserted the completely relativistic version of the Larmor power into that. So now I write 6 here, even though I wrote 5 here. The reason is, once more, that this is the Larmor power emitted by the source at the retarded time t prime. This is not exactly what we need here, because here we need the Larmor power arriving at the observer at time t. And therefore, another factor, 1 minus e times beta, appears here, and we get, fortunately I have to say, we get the 1 over 1 minus e times beta to the power of 6 here. Okay, fine. Then we have that here. All right. Now I'm going to use Plancherel's theorem. I'm calling this expression here f of t absolute square. Then I can write this by Plancherel's identity as f twiddle of omega absolute square. This should be a vector here. All right. This is the key identity we are using. So we are using that the absolute square of a Fourier transform integrated over the Fourier conjugate variable equals the absolute square of the original function. Sorry. And from that we can now read off the spectrum, that is the way how the energy is distributed over frequency, dE d omega is q squared divided by 4 pi c times 2 pi, so we have 8 pi square f vector tilde squared. So that's the way how we get the spectrum. Now, this means that for this expression here, the f of t, we need the Fourier transform f tilde of omega. And this is surprisingly simple. And this is what we are now going to do. So the key point is now that we have to calculate this function here. So let me write this down, this Fourier transformed vector as a function of frequency. And by definition, this is going to be f of t e to the minus I omega t, integrated from minus infinity to plus infinity. And so this is, first of all, integral over dt e times e minus beta times beta dot divided by 1 minus e times beta to the power of 3. That's the function f that we have above, just by Larmore's formula. And then we have that. Okay, this looks awfully complicated, but it is not at all. For the following reasons. The first is, of course, instead of using the time, the observer's time t here, we can use the retarded time t prime. This has a massive advantage because then we will get the Jacobian of dt prime with respect to dt, and this cancels one of these factors, 1 minus e times beta. So that would mean that we get rid of one of them already. So let me transform the observer's time to the retarded time. Then this is now to the power of 2 here. But now I have to insert here in the Fourier phase the observer's time expressed by the retarded time. So let me write this down. The retarded time is given by the observer's time minus r over c, right? I need to take into account that the light needs some time to travel from the source to the observer, and the time it needs to travel is the distance r divided by the speed of light. All right, now I have to insert t as a function of t prime. So this is t prime plus r over c. And r depends in a delicate way on t prime. This we need to take into account. Okay, now, as announced last time, a miracle appears. Namely that this expression with the braces underneath is a total time derivative, a total derivative with respect to retarded time. Namely, this is, I claim, if you don't believe it, which you shouldn't, then you can calculate this, and you should. But you need at least about 2 hours. And this is too precious for me to do right now. So I'm just claiming that, and I'm asking you to test that. I'm claiming that this is the total derivative with respect to retarded time of the quantity of the expression that I wrote down here. E cross beta divided by 1 minus E times beta in a single power. Yes? All right. Do you believe this? Or should we go back to that? All right. This is the Larmor power per unit retarded time, per unit t prime. What we need here is the Larmor power per unit observer's time. And this gives rise to another factor of 1 minus E times beta. So this is why the power of 6 appears here instead of the power of 5 over there. Okay? Good. So now I need to take the square root of this expression because I need its Fourier transform. So therefore, I have a single power of the numerator and the third power of the denominator. So this is how I arrive here. Now I transform to retarded time. And this is why one of these factors cancels again. So now I'm back at 2. Okay. Okay, then I show you. This is a piece of art. I'm not sure whether I'm allowed to write on this piece of art. Look, we had t prime is t minus r over c. R is, and I'm deliberately writing it like this, rj square root, right, where I'm implying Einstein's sum convention. And the components rj are xj minus x0, that's the trajectory of the particle, j of t prime. All right? Good. Now I need to take the derivative of t prime with respect to t. This is 1 minus 1 over c. Now the derivative of capital R with respect to t, not t prime, depends on t prime, right? But I need to take the derivative with respect to t. So what am I going to do? I need to take the derivative of that first. This is rj over r. Then I need to take the derivative of rj with respect to t. This is minus x0j dot, where this dot now means the derivative of x0j with respect to t prime. Now I need to take dt prime with respect to dt, and I'm there. Are you with me? All right. So I have the same expression here and there. I need to solve for that. But this is c times minus c times beta. Right? This is the velocity of the source charge at the retarded time. So this is 1 plus, the c cancels. Rj over r is the j component of the unit vector E. So this is Ej times beta j times dt prime with respect to dt. Now I'm going to solve this equation for dt prime with respect to dt. So I get 1 minus e times beta dt prime with respect to dt plus 1. And this is why you get these factors of 1 minus e times beta in transforming back and forth, right? And once I'm transforming in the one direction, once I'm transforming the other direction. That's important here. All right? And this is how we arrive at the power of 2 here by transforming to the retarded time. Okay, so I'm claiming that this is this time derivative here with respect to the retarded time, but now I can obviously use partial integration here. Okay, let's return to the piece of art. Okay, now I'm going to continue here, and I'm going to write the Fourier transform of f as a function of omega as, first of all, dt prime total time derivative of e cross beta divided by 1 minus e times beta e to the minus I omega t prime plus r over c. Okay, good. Now what is called for is obviously partial integration. So I'm transferring the time derivative to the Fourier phase factor. This gives me a minus sign. I'm ignoring boundary terms because I say at plus or minus infinity the radiation is over. Then I can write first of all the underived factor here. And now I need to have the time derivative, the derivative with respect to t prime of this thing here, which gives me a minus I omega 1 plus 1 over c derivative of r with respect to t prime. This is the time derivative of the Fourier factor, and the Fourier factor remains. And now another miracle appears. Because, can you read this? I mean, okay. dt prime r, see, we calculated this already. Calculating it again. As before, this is rj over r from the derivative of r with respect to rj. Then I have the time derivative of rj. This is minus x0 j dot. Now I can stop because I'm taking the derivative with respect to retarded time. Right? Before we had to transform. Now we don't because we are taking the derivative with respect to t prime. So this is minus c e times beta. Okay? In other words, the only remaining denominator here, 1 minus e times beta, is also cancelled. Okay? So I can write this as I times omega. These are factors that do not depend on t prime anymore. Then what I have to integrate over is just this expression here. 1 plus 1 over c dt prime r is 1 minus e times beta, cancels this thing. What remains is that. Okay, at this point, in order to move on, we need to know how beta depends on t prime and how r depends on t prime, and then the trouble starts, right? But this is a really very simple expression for the spectrum we are getting. One can even further simplify that, because if you apply Grassmann's identity, which you wrongly found on the problem sheet, to write this in a different way, right? This would be scalar product of E times beta times E minus beta. What is this? That's a very intuitive quantity. Suppose you had the different sign, right? Beta minus E times beta times E. You would first project beta on E. That's the line of sight component of the velocity. You multiply this with a vector pointing towards you. That's the line of sight component in the direction of the line of sight. You subtract this from beta. What remains is the perpendicular component. Right? So this is very simply minus beta perpendicular. So we could even further simplify this expression, right? But let's leave it at that. Okay. Now we need to add one more word about the Fourier phase here, because that should also be simplified. So finally, I'm looking at the distance r between the source at the retarded time and the observer once more. And I say, well, this is obviously the unit vector from the source to me times the vectorial distance here. And now I'm going to split up that distance in the following way. So I'm assuming that the charge is orbiting about some point. And I'm taking the distance of that point to us, and I call it small r, small vector r. Then the charge may be here. It's orbiting about this point. And I call the vector from the reference point of that orbit to the charge small x. So then the vector r is obviously minus x plus r. So this is E times r minus x. This doesn't seem to be a big help, right? But it is. E times r is just r. That's the separation, and we assume this to be constant. That's the separation of the reference point of the charge's orbit. And we have minus E times x, right? Now I need to project the orbit of the particle on the unit vector in the line of sight direction. All right, I'm doing that because then I'm getting a constant contribution to the phase factor here. And I can ignore that because I have to take the absolute value squared of our Fourier transform later. Okay? So finally I can write Fourier transform vector f as a function of omega. This is I omega dt prime E cross beta e to the power of minus I omega t prime, now minus 1 over c e times x. You see, in comparison to what I wrote earlier, this is not quite correct, right? Because I'm ignoring the constant phase factor that I just pulled out. Nonetheless, if we continue calculating with this expression here, we do not make a mistake because that constant phase factor drops out. So this is the final equation that we need in order to calculate a spectrum. And you see, in general, this is, or conceptually, this is really simple. Right? This is just the negative, but since we have to take the absolute square, the sign doesn't matter. So this is just the perpendicular component of the particle's velocity in units of c, and then integrated over this phase factor. And now you see, in calculating spectra, this is the main problem, because here you have to insert now the orbit of the particle in the Fourier phase. And this is why calculation of spectra can get rather difficult, but we are going to make it easy. All right? So now we can return to our expression for the spectrum that we had here, and insert the Fourier transform that we just calculated. So let me do that. So this is our main result for the moment. It's a solid angle differentiated expression for the for the received spectrum, q square divided by 8 pi square c hope this is correct. Now, absolute value of integral over dt prime e cross beta e to the minus I omega t prime minus e times x divided by c. And we had factored out the factor omega, which now appears as a factor of omega squared here. The rest, right, the I and the constant phase factor and so on, they disappear. And here we have our expression for the spectrum. All right. Very nice, right? Now you dream of an orbit. You insert the orbit here, you do the Fourier transform, you have the spectrum. In many cases, it is sufficient to retrace all these steps with a non-relativistic Larmor power, which then arrives at a much simpler equation. So let me do this once more, starting here, again, but now using the non-relativistic differential Larmor power here. So in the non-relativistic case, which is often sufficient, but not always, you write dE, d omega, again beginning here inserting that using Planck-Jorel's equation, getting q squared divided by 8 pi square c. Now, this expression here, Fourier transformed, squared. This is now the differential spectrum. If, on the other hand, you do not need the solid angle information here, you get a further simplification. Then all we need to do is that, right? We need to integrate over p. Now I can insert the non-relativistic complete Larmor power. So this is 2q squared divided by 3c. And now let me write the spectrum right away. Now this would be you know what I mean, right? Beta dot tilde. So that's the acceleration Fourier transformed. I can move on a bit. So this is q squared divided by 3 pi c. Something's wrong here. Well, in any case, q squared divided by 3 pi c, let's say cubed here, because I want to pull the factor c out of the acceleration. Now we just have the Fourier transformed acceleration as a function of omega absolute squared. Now this is easy. Let us use that right away. Right? This is now the spectrum of a non-relativistically moving charge without the solid angle information. And there you see, all right, all you need to do is calculate the acceleration of the particle and Fourier transform it. So let's make a simple example for that. And say, suppose we want to play tennis at night in complete darkness. It must be a challenge, right? And we play with an electrically charged tennis ball. That makes it funny, right? Because then you hit the ball, that means you accelerate it, and then the ball is radiating. So for a brief moment you will see something. Now let's see what the spectrum is. The spectrum of the charged tennis ball at night. Takes some effort to destroy a piece of art, I notice. Okay. So let's say we have the following acceleration profile. As a function of time. between times minus tau over 2 and plus tau over 2, we have a constant acceleration. Let's call that A0. And at all other times, the acceleration is 0. Okay, so what's the Fourier transform of that? Well, this is now the integral from minus tau over 2 to plus tau over 2. A0 times e to the minus I omega t dt. So this is A0 divided by minus I omega e to the minus I omega tau over 2 minus e to the plus I omega tau over 2. Now you see, if I change the minus sign, right, in response to that minus sign out front, I'm subtracting a complex conjugate number from a complex number. So what remains is just 2 times the imaginary part, or 2 times I times the imaginary part. So this is 2A0 divided by omega of the sine of omega times tau over 2. Or, if you wish, extended by a factor of tau. Okay, so let's now insert this into our expression for the spectrum. Now the solid angle integrated spectrum. This is now going to be q squared divided by 3 pi c cubed. And now A0 square sine square omega tau over 2 divided by omega tau over 2 square times tau square. I'm writing it in this awkward way because the combination of these expressions here just gives you a spherical Bessel function. So this would be q square A0 square divided by 3 pi c cubed J0 square of omega tau over 2 times tau square. Of course, if tau goes to 0, right, you don't accelerate at all, and the spectrum is 0. Otherwise, you see that if you look at the spherical Bessel function, it looks like this. You see that you get a relatively sharply peaked spectrum with a width that is set by 1 over tau. Okay? This is just an example for the non-relativistic Larmor spectrum that we have calculated up there. And so you see, you have now several ways of calculating the spectrum of an accelerated charge. In the non-relativistic limit, it's a very simple expression. It's just it's just given by the Fourier transformed acceleration squared. And if you have a relativistically moving charge, it's given by the equation above. And now, of course, we need to use that. Right? Let me say one more word about the Fourier transform of the acceleration. Because that can still be expressed in a simpler way. And for that, I'm going to write the acceleration as a function of time and express it by its Fourier transform. But first, I say, okay, that's the second time derivative of x of t. the second time derivative of the Fourier transform of the orbit itself. Now you see that you can easily carry out the time derivative because it acts only on the Fourier phase. It gives you a factor of I times omega squared. So this is minus integral d omega over 2 pi omega squared Fourier transform of the orbit e to the I omega t. And now you Fourier transform this back. And you see that the Fourier transform of the acceleration is just minus omega squared times the Fourier transform of the orbit itself. And sometimes one of them is easier than the other, and then just think about this relation and use what is easier. All right. I suggest that I now wipe the board and you have a break, and then we move on. And I would like to move on towards a point charge moving in a magnetic field. And this I would like to consider in a fully relativistic way. And that's going to be even more exciting than the non-relativistic way. For several reasons, you will see that. Okay, but first of all, 5 minutes break, I wipe the board, and then we move on. ready to move on? Okay. So as I said, the situation I would now like to consider is the following. I assume that I have a magnetic field and I have a point charge moving in that magnetic field. It should move relativistically because that's the fun of it now. But what's the equation of motion? What's the force acting on this source, on this charge? Opinions, please. The magnetic force. Indeed, yes. Do we have a formula? For the magnetic part of the Lorentz force? Help. What should I write down? Could you say again? Q. How would you go on? I have 1 over c here because of our choice of units. Sorry, my choice of unit. But that's the magnetic part of the Lorentz force. And this acts on here's the gamma. This acts on this expression here. It's the relativistic version of the Lorentz force equation. All right. Do I have to take the time derivative of the gamma now? And that would be awful. But do I?
Use the proper time.
If I use the proper time, I could drop the gamma. But I want to use coordinate time. Does gamma change in time?
It doesn't, because the force is perpendicular to the direction.
Exactly right. The only thing that enters into gamma is the absolute value of the velocity. But that doesn't change because the Lorentz force acts perpendicular to the velocity. And therefore the absolute value of the velocity does not change, and therefore gamma does not change either. So that's nice, isn't it? Therefore I can directly write dv dt is gamma qb divided by gamma MEC. All right. Vector product of the velocity with the direction vector of b, and I'm orienting the b field now along the z direction. In other words, I'm just rotating the coordinate frame such that the z direction points into the direction of the b field. Okay. This means that the z component of the velocity is obviously not changed. Right? Because the z component of the velocity with a vector product with Ez taken just returns 0. So I only need to consider Vx and Vy. So this means that dv dt is this quantity here, qb, divided by gamma MEC, is Vx times Ex plus Vy times Ey, vector product taken with Ez. So Ex Ez is minus Ey, Ey Ez is Ex. So this is qb divided by gamma MEC Vy Ex minus Vx Ey. Okay, now I project on Ex and Ey and I get the two equations of motion for the two remaining components. Vz is just constant. So I get Vx dot is QB divided by gamma MEC Vy, and Vy dot is minus QB divided by gamma MEC Vx. And now you have several ways of solving that system, right? Either you combine Vx and Vy to a single complex velocity and solve this first order differential equation directly. Okay, you can do that. The other thing is you take another time derivative. Now use that equation and you find Vx double dot plus QB divided by gamma MEC square, Vx equals 0. You find an oscillator equation that contains a frequency squared, so you can read off the frequency of the circular frequency of the orbit, and you find that the circular frequency called the Larmor frequency, Larmor again. By the way, have you ever heard of Larmor? Joseph Larmor, Irish physicist. Was the first to find the Lorentz transform, by the way. That's why it's called Lorentz transform. Omega L is QB divided by gamma MEC. Sometimes you find the version without the gamma, then it's called the cyclotron frequency. But this is called the synchrotron frequency or the Larmor frequency. All right. So with that angular frequency, our charge is going to go around in circles. Okay. Of course, if we have an electron, we would have minus E here, but this doesn't matter for now. Okay. Good. Now, let's calculate the Larmor power. Not the differential Larmor power, not the spectrum yet, but the Larmor power. Right? Regardless of how the energy that this electron is now going to give away is distributed over solid angle or is distributed over frequency, what is that power? It's a beautiful formula that's going to come out. So that's the Larmor power in this case, or the synchrotron power for our specialization. Synchrotron power. Okay, what do we need? We need a total expression for the Larmor power. I'm just copying again what we had on the board in the beginning of this lecture and also last time. Now, of course, you can parameterize the circular orbit for the particle and calculate beta and so forth. But this is much easier because if you have an oscillator, right, with velocity beta, beta dot just has to be omega L times beta. So I'm using that beta dot is omega L times beta. And I'm also using that on a circular orbit, beta dot must be perpendicular to beta. So if I take the absolute value of this, that's just going to be beta square omega L. What else should it be? All right, now let's insert that And you see this is 2q squared divided by 3c. Now, omega L square appears in both terms. Then we have beta square minus beta to the 4th power. Oh dear. Oh, I forgot the gamma to the power of 6 here, and the Lorentz factor here. Okay, now I factor beta square out, and 1 minus beta square remains. But 1 minus beta square is gamma to the power of 4. Gamma squared, sorry. So what remains is this. Now, if we had an extremely relativistic charge, gamma would be very large and beta would be very close to 1, and then we could even drop the beta square here and leave it out, right, for an extremely relativistic charge. Okay, essentially we are done, right? Essentially we have calculated the Larmor power for a single charge with charge q in this magnetic field. But let me now reinsert the expression for the Larmor frequency and just massage the constants a little bit. So that's going to be 2q squared divided by 3c, all right? Then the formula for omega L squared. So that's another q square, b square divided by gamma square, me square, c square. Okay, I just copied the expression for the Larmor frequency. Beta squared, aha, we had a factor of gamma to the power of 4. So that goes away and we are left with a factor of gamma squared. Okay, but now I would like to have an 8 pi here because I like the expression 8 pi. Then I divide 4 pi out here. Okay, just for the fun of it. So now, what do you find? You find 8 pi over 3 q to the power of 4 me square c to the power of 4. I'm making a mistake here. I only have c to the power of 3 here, so I have to correct this. Then what remains is a p square over 4 pi beta square gamma square. Do you recall what that is? If I insert the electron charge, that's just the classical electron radius squared, times the factor of 8 pi over 3, that's a Thomson cross-section. That's all of that. B square over 4 pi is the energy density in the magnetic field. So that's the energy density UB of the magnetic field times beta square times gamma square. Now again, if you have an extremely relativistic charge, beta square goes to 1, and you see that this is a very, very intuitive expression here. With the Thomson cross-section, the electron is interacting with the energy density of the magnetic field here. And you get a Lorentz boost of a factor of gamma squared. All right, this I wanted to show you. That's the very intuitive expression for the synchrotron power. All right, now we know how much the electron is radiating per unit time. But now we want to know where does it radiate this to? And how does that radiation distribute over frequency? So now I need to look at the differential Thomson cross-section, sorry, the differential Larmor power. So let me write this down again. because I need to come back to an argument that I made when I first wrote this down, right? There's a factor of the fifth power here. So now I want to have a look at what this is. Okay. Obviously, if the velocity points in my direction and the velocity is very close to the speed of light, then this is an extremely large number. If the velocity is perpendicular to the line of sight direction, this is just 1. So the more relativistic this charge becomes, the more the radiation is beamed towards the direction of motion of the charge. So I'm expecting, and you saw this also in the Jupyter notebook, I'm expecting that there's a radiation cone, so to speak, which points into the forward direction of the motion of the charge. And that should be relatively narrow. And I want to know how narrow is it. Okay? So I'm imagining there's our electron. Electron is moving somewhere here. I probably get a radiation cone, a radiation club here. Whose opening angle I call theta now. And I want to have an estimate for how large this angle or how small this angle actually is. Okay. Let me write it this way. This is obviously less or equal than 1 over 1 minus beta. Right. There's a cosine in between, and the maximum value of this cosine is 1. All right. I'm going to rewrite this as 1 minus cosine theta times beta less or equal 1 over 1 minus beta. Now I want to know, how can I constrain the angle theta? And I want to know, or I do this by asking, at what angle theta has this factor dropped to half its maximum value? Okay, so I want to know at what angle theta is this equal to 1 over 2 times 1 minus beta? Right, the maximum power, or the maximum of this factor is 1 over 1 minus beta, and I want to know what's the half value, right? At what angle does this radiation cone here reach half its maximum value? Okay, so I can turn this around. I can say 1 minus cosine theta times beta equals 2 times 1 minus beta. And now I make an approximation for the angle theta because I can expect it to be very small. So I say 1 minus theta squared over 2 times beta approximately equal 2 times 1 minus beta. In other words, I'm using the second order Taylor expansion for the cosine of theta, right? Because theta should be small. Okay. Well. Good. So I get 1 minus beta. I get plus theta squared over 2 times beta. Must be approximately equal to 2 times 1 minus beta. Okay, or theta squared approximately equal to, I subtract 1 minus beta on both sides, and I get 2 divided by beta, 1 minus beta, square root. So that's an estimate for the angle theta. Now you see, okay, if beta approaches 1, well, then the angle is approximately 0, and that's what we expected. But how large is it actually? So, of course, if I just say beta is approximately 1, then I get 0, and I don't want that. So this is obviously too coarse as an approximation. So let me do it like that. In other words, I'm expanding the 1 minus beta by 1 plus beta. Well, does this help in any way? Well, 1 minus beta squared is 1 over gamma squared. And what remains is this expression here, 1 over beta times 1 plus beta. Now at this point, I can safely make the approximation beta equals 1, right? Because here I don't have to subtract beta from 1, getting an awkwardly small number. So I can just approximate this as 1 over 2. And I get theta is approximately 1 over gamma. Okay, in other words, if I have a relativistically moving charge with let's say, a Lorentz factor of 1,000, then the radiation is beamed into a very, very narrow cone. So suppose our electron is running around in a circle. What else should it do? Then what do we see of this electron? Most of the time, nothing, right? Because we will see the electron only when its narrow radiation cone hits us. For this to happen, we have to be almost exactly in the orbital plane of the electron. Suppose we are, right? So the electron is going around in a circle very fast, right? Like this. We have to be in the same plane, or just a little bit above or below. Let's assume we are in that plane. Then what do we see? We see very narrow blips of light, very narrow lightnings. Okay. How narrow? How narrow are they going to be in time? Well, we know how wide the angle is going to be. It's 1 over gamma. In order to cover that angle, the electron needs how long? It's given by the Larmor frequency, right? So it's theta over omega L. Right? Then you can calculate the very little time interval during which you are on the way. What spectrum do we expect now? There is a single frequency defining the orbit of the electron. But what spectrum do you see in that situation? Very short time signal in Fourier space. What spectrum? Yes?
Shouldn't it be a sine wave or like cosine wave?
Suppose, so the answer was a sine wave. Let's see. Suppose the angle theta was infinitely small. Then the signal in time would be a delta function, right? What's the Fourier transform? It's a constant. Would be a constant, right? So even though the orbit of the electron is given by just a single frequency, you do not expect a spectrum with a single frequency just because you see the signal of the electron in a very short time. What you see is a very, very broad spectrum, right? It's going to be even broader the more relativistic the electron is. That's the key point. The rest is just a boring calculation now. But you see, that is important. There is an enormous beaming in the Larmor power. Because of that, we see the radiation of the electron only in a very narrow cone. Because of that, we see the radiation of the electron split up into very, very short time signals. Right? And because of Heisenberg's uncertainty principle, right, in frequency, this is an enormously broad thing. Okay? And this is totally different if you had a non-relativistic charge. Right? If you had a non-relativistic charge going around very slowly, then you would have no beaming effects, and you will get this as a homework. All right, but that's the key point. Now let's have a look at the spectrum. What's it like? So in order to be specific, let's say here is Ez, that's the direction of the magnetic field. Now the electron is obviously going around in the xy plane. So let's say we are also in the xy plane, because otherwise we don't see anything. And then the spectrum is easily calculated, but rather boring. So the electron is going around here. Let's say it's traveling in the mathematically positive sense. Now you can find out yourself where the magnetic field has to point. All right, and we are going to see this electron only when its radiation cone is hitting us. And the radiation cone will point in the forward direction of the motion of the electron. So, in other words, we are going to see the electron along its circular orbit only when its tangential direction is almost hitting us. Oh dear, that's a problem. Right? What we calculated before was we have to evaluate this expression. And we said this is minus the perpendicular direction of the velocity, perpendicular to the line of sight. So this means we will never see the electron in full glory, but only very shortly before the radiation cone reaches its maximum, and very shortly thereafter. Right? Because the electron must have a velocity component perpendicular to the direction towards us in order to radiate at all its spectrum into our direction. Okay, good. Let's say that's the beta y component. I don't care about the sign because we will have to take the square anyway afterwards. Let me call this beta times sine phi times Ey, where phi now is this angle here. Right? I'm introducing an azimuthal angle in the orbital plane such that if the electron points directly or moves directly towards us, phi equals 0. Okay. Now what do we have to calculate? We have to calculate this expression here. Let me drop this factor of I because it's going away anyway. So this is all that is left of our E cross beta that appears in the equation for our spectrum. And we have e to the minus I omega t prime minus e times x divided by c. Okay. Now we said we have to integrate here, or we have to insert here into the Fourier phase the orbit of the electron. But then again, we have to project the orbit of the electron onto the axis pointing towards us. That's the x-axis. So let's have a look at the Fourier phase psi. The Fourier phase psi is omega times t prime minus 1 over c e times x. So this is omega t prime minus 1 over c. Okay, that's the projection of the electron's position on the x-axis. So if phi equals 0, this projection is 0. So we have x times sine phi here as well. All right, now we need to establish a relation between the time t prime that we have to integrate over and the angle phi that we have to use to parameterize the integrand. But this is easy. This is easy because we know that x times the Larmor frequency, so this is now, x is now the radius of the electron's orbit, times the Larmor frequency, that's the electron's velocity, divided by c. This is beta. We know this is approximately 1, and we know that the angle phi is omega L times t prime if we choose the origin of the time t prime, the origin of the retarded time, such that the angle phi is 0 at time t prime equals 0. Okay. Now we know that we are going to see the electron only, and this means that the whole integrand will have an appreciable magnitude only if the angle phi is very small. And if it's large, we are not hit by the radiation cone. If it's 0, we are not hit by the radiation cone either, right? But it has to be small in any way. So I can approximate sine phi, approximately phi minus phi cubed over 6. So this is omega Lt prime 1 minus omega L squared t prime square divided by 6. Okay. Now I'm going to use the third order Taylor expansion for phi. Yes? Could you say again? This one? Here you mean? No, because I've pulled omega Lt prime out. See, so I'm factoring phi out from this expression here. All right, so now I'm going to use the third order Taylor expansion that's written down here in the Fourier phase, and I'm using the first order Taylor expansion in the integrand. I have to do this because otherwise the rapid oscillation in the Fourier phase would cancel everything I need. Okay, so in this approximation, I can write, this is now an integral, omega times an integral over dt prime. Beta. Let's set beta to 1. Then I have sine phi. I'm approximating this as omega L times T prime. I have this direction here. That's interesting as well. Then I have minus I times psi, just to abbreviate the Fourier phase. And for the Fourier phase, I'm going to use this kind of approximation here. All right. Now let me introduce a new time coordinate. So I want this to be tau squared over 2. So I'm approximating tau is omega L T prime what do I want there? It would be a factor of square root 3 that I'm not expecting here. Let me go a little bit more careful about this Fourier phase here. So I have psi is omega T prime plus x over c omega LT prime 1 minus omega LT prime squared divided by 6. Okay. So this is omega T prime factored out. Now I have 1 plus x times omega L divided by omega c. Omega c. Now I'm here. Now I have 1 minus omega L squared T prime squared divided by 6. All right, that's now the Fourier phase. Now I'm going to use that x times omega L divided by c. This expression here is beta. And then I can set this to 1. Okay, so let me return to that. Going to write the Fourier phase again as omega T prime 1 plus. There must be something wrong there. Sorry, I'm confusing myself. Let me return to omega.
Confused in the last term on the upper blackboard, there's an omega in the last, or not, last term in the, below the French line that we don't quite know where it.
Okay, good. Let's return to that. I think we agree on this point. All right, now this is the x component of the orbit, as we said. So this is 1 over c x times sine phi, with the brackets like this. And I think we agree on that, do we? Okay, so that's omega t prime minus x over c. Now, sine phi, we said, is omega lt prime 1 minus omega L squared T prime squared divided by 6. So in other words, I'm now inserting here, instead of the sine phi, the third order Taylor expansion for the sine. Okay. Now I want to pull omega T prime out. Then I have 1 minus x omega L, of course. Oh dear. All right. Now I identify this with beta. That's an approximation here, and this third order Taylor. So now I have 1 minus beta, and here I need to be careful because I subtract beta from 1. Now plus beta times this, but here I can approximate beta equals 1, and I'm getting this. Okay. Now again, I'm using that 1 minus beta is 1 minus beta squared divided by 1 plus beta is 1 minus beta squared divided by 2, approximately 1 over 2. No, this is equal now. 1 over 2 times gamma squared. Okay, now I'm back on track. So this is omega t prime divided by 2. Now I have 1 over gamma squared plus omega L squared T prime squared divided by 3, right? Because I factored a factor of 2 out. Now I'm calling tau equals omega L times T prime. I should in fact multiply this with a gamma here. Then I have omega t prime divided by 2 gamma squared, 1 plus tau squared divided by 3. All right. And here I'm also inserting now t prime equals tau divided by omega L gamma. So this is omega times tau divided by 2 times omega L gamma cubed, 1 plus tau squared over 3. Okay, now I have essentially the Fourier phase in the form that I wanted it to be. Now let me just reassemble the equation that we need to address next time again, and then stop for today. So I want to return to the Fourier transform function f. So let me just copy that. That's an omega. Now an integral over t prime. I need to replace the integral over t prime by an integral over tau, right? So I say d tau equals gamma omega L dt prime. So the dt prime is integral d tau divided by gamma omega L. Then I have just the sine phi over there, which I approximate as omega L times t prime, but omega L times t prime is tau divided by gamma. And then I just have the Fourier phase e to the minus I psi. All right. So what remains is an integral of this form here, 1 over gamma square omega over omega L integral d tau times e to the minus I psi. This goes from minus infinity to plus infinity. And this is where I wanted to arrive, because this now is a certain type of Bessel function. And that's where I wanted to restart next time again. All right, let me briefly summarize what I did, and sorry for the confusion in the meantime. We found a general expression for the spectrum of a relativistically moving charge. We wanted to apply this to an electron going around at a relativistic speed in the magnetic field. We saw that in this case, the radiation of the electron is beamed very strongly into the forward direction of the motion of the electron. And therefore, we could very strongly simplify the expressions we had. Because only during a very short time interval along the orbit, and that is only during a very narrow interval in the azimuthal angle, we need to solve this the integral for our spectrum anyway. In that very narrow interval for either the azimuthal angle phi or the time t prime, we can approximate the orbits, right? We can approximate the trigonometric functions that appear in the calculation. And this allowed us to finally arrive at this expression. And there we will restart next time. The idea is that because you see the electron at each orbit only during a very narrow time interval, the spectrum becomes very broad. And the more relativistic the electron is moving, the broader the spectrum gets. All right. Do you have questions before we stop? Not the case. Then have a nice weekend.